This is the second video for the improper integrals lesson. In this video, I'm gonna try and fit 3 examples in here. 2 of them are gonna build off one another, and the last one is gonna involve integration by parts. So for our first example, let's consider the function x times e to the negative x squared. And this is an improper integral of the first case I talked about because we're still talking about an integral that has a limit of integration that's infinity. So when I graph this is not a function we see a lot. I zoomed in a lot here, like my window, my y, min, and max are only -1 to 1. So you can see that this is a very low function. It doesn't go very high up, less than a half here. And you can see there's a horizontal asymptote at 0, so it gets to the x-axis very quickly. Let's go ahead and see if I do the area from 1 all the way to infinity, is this going to converge or diverge? Can I say that the area under the curve is an actual number, or is it infinite? So I drew the graph here. Never underestimate the power of a good visual. It's going to help a lot whenever you do the more complicated ones. So what I'm going to do is, like last time, I'm going to do the integral from 1 to b. I'm going to send b to infinity at the very end after I've done all my work with taking the antiderivative, etc. And now you have to decide, all right, well, this integrand looks a little bit complicated. I can't just do it in my head. It's not a basic one. Let's see, we have partial fraction, but it's not a denominator. We have parts and we have u sub. Notice here I have a term and a form of its derivative there. So I'm going to do a u substitution. Now these problems get a little bit complicated because I have a limit, I have b, I'm doing u sub at the same time. Just forget about everything for a minute and just do u sub right underneath here. And remember, the limit is just hanging out right now. Don't worry about the fact that I have a limit out front. Don't get overwhelmed by all this notation because it's going to be a lot, especially for the more complicated ones. Just take it one step at a time here. Let's let u be the term with the higher power. Du is -2x dx. I needed to say just x dx, so I'm going to divide by -2. And now I have the x dx that I really want. So I'm going to go ahead and rewrite this with my u's. What I have done right here is I've rewritten my integrand so it's entirely in u talk. Now this is where you have to make a choice. I'm going to make a recommendation. I'm going to show you both ways and you're going to pick which way you want to do. Before, when we did a definite u sub problem, I did that whole Uganda thing and you had to translate everything, including your limits of integration down here and up here, to u talk. And then you didn't have to plug x back in. I've done a bunch of these problems and I actually have found it easier to translate your integrand to u, but keep your limits in x talk. And watch what happens here. I'm going to do it the way I used to do it over here. I don't know. I just feel like there's a whole lot going on translating these limits of integration as well. And then there's a b here and that bothers me. But again, it's your problem. You're the one who's going to do these on the AP exam, so you decide. I will typically translate the integrand and not the limits. Okay, then in just a second, I'm going to go back and do it this way. So you can see it is the same. It's only 2 steps that are going to be different. So anyway, I've rewritten my integrand in u talk so that I can easily take this antiderivative. I haven't even done an antiderivative yet. These limits of integration, I'm putting x here to emphasize that these are x values, not u values. I did not translate these. So -1/2 is a constant. The antiderivative of e to the u is e to the u. This is still x equals 1 to x equals b. Now, I can't plug these values in here to do FTC part 1 because this is u and these are x's. So what I'm going to do is something that I didn't really do before. Some of you actually did this on your own. It works out in the end. I'm going to go back now that I've done the antiderivative. So u did his job. Hooray, we found the antiderivative. U is done. He can go. We can bring x back in. So u was -x squared. So x equals 1 to x equals b. So now, again, we're still writing this limit over and over again. I have -1/2. And when I plug b in here, I have e to the -b squared minus, I pulled the -1/2 out, e to the -1 squared is just e to the -1. So let's go up here and see, all right, if you had done it the way that I told you to do before, will we get the same thing? Let me just prove to you that we will, and then you can decide which way you like better. So I still translated my integrand to u talk. Then I translated my limits of integration to u talk. This is going to eliminate the need to go back to x, which I did right here. So when x is 1, here's my little dictionary. Whoop. When x is 1, u is negative 1. When x is b, u is negative b squared. So now I have the limit as b goes to infinity of I'm going to do the antideriv right now. The antideriv of e to the u is e to the u. I'm going from negative 1 to, negative b squared. These are u values here. So I'm going to move back down here. So I have the limit as b goes to infinity of negative 1/2. Leave the negative 1/2 on the outside. Now, since these are u values, I'm going to plug them right in for u. So it's e to the negative b squared minus e to the negative 1. And look, it's the same exact thing. It's just a couple steps that are different. Again, you're going to decide, would you rather go from u back to x and not mess with the limits of integration, or would you rather change the limits of integration and not go back to x? Same thing in the end. So I'm going to clean this up. Every time I clean up, remember, I always write negative exponents in the denominator because it makes it a lot easier to think about what happens when I plug b in. Now that I've done FTC part 1, I've cleaned it up, I'm now ready to do direct substitution with my limit. I'm going to think, okay, if b was infinity, I can't plug anything in here, so if this was e to some larger and larger power, what would this term go to? Well, 1 divided by an increasingly large number is just 0. You can't plug b in anywhere else, so then this is just negative 1/2. 0 minus 1 over e is negative 1 over e, so 1 over 2e. The limit exists, the integral converges, so the integral converges, and the area under the curve from 1 all the way to infinity is 1 over 2e. So this happens to decrease fast enough, which you can kind of see when you look at this. It decreases very quickly. So that's why the area is finite. Now let's take a look at another problem. Instead of going from 1 to infinity, let's do the same exact problem, but go from negative infinity to infinity. So we're now going to type this type here. We're still like in the first type of problem, but both our limits of integration are going to involve infinity. Visually, what our next problem is going to be is the same exact curve we did before, except this time I'm going from negative 20 to 20 on the x-axis, just to represent negative infinity all the way to infinity. So I want the area underneath the entire curve, so the negative and positive area. When I write it down, what it looks like is this here. So write down your next example. The trick to doing this, if you have a negative infinity and an infinity as your limits of integration, is we're going to split this single integral up into 2 integrals using this property of integrals. Remember, there was 5 properties of definite integrals. This is one of them. If I go from a to c, I can pick a number in between a and c and split it up as long as these two numbers are the same. So typically the problems like this are going to split it up at 0, and that makes sense here because I have an x-intercept, and that 0 seems to cut the graph in half here between negative signed area and positive signed area. So I want this unbounded region here. We're going to see if it actually is bounded or not. Now, you do not want to just assume that the area is 0. That's very important here. Visually, what it looks like is, oh, this negative area and this positive area, they're symmetric. This is an odd function. And remember, for an odd function, if you go from negative c to c for an odd function, you're always going to get 0 because of the symmetry. Don't assume that case for improper integrals. You're going to get yourself into trouble for some problems. So we're still going to do it all out. We're going to split it up at 0. And check this out. We get 2 for the price of 1 here. We now get double the fun. We have 2 improper integrals. This one, we've already done types like this before. This should be quick. This one, though, we have not done over the lower bound is infinity yet. In this case, since we have double the work here, let's let this one be b. So I'm going to go from b to 0. Instead of starting at 0 and going all the way to negative infinity, let's call this guy b and let b go to negative infinity. And we should really use a different letter here since it's the same problem. We want to be clear. I don't know, we can do m. It really doesn't matter what the variable is. So I'm going to call that m. So let's say, all right, this is m, and let's let m go to infinity. So I'm going to do all of this work in black and all of this work in red to keep them separate. So again, we're really just doing 2 different improper integrals here. Now, again, we already know what this antiderivative is. Let's not do more work than we have to. Let's just go right up here and see that when I did this same exact problem, the same integrand, I ended up with negative 1/2 e to the negative x squared, going from the lower to the upper limit of integration. So let's take that and let's bring that right down here so we don't have to do u sub again. What I've done here is the first half of the first fundamental theorem of calculus. I've done the antideriv, which we already did before. I really just transferred it down here, negative 1/2 e to the negative x squared. The integral and the dx are gone for both because they go, as soon as I do the antideriv, they disappear. I'm going from b to 0 here and from 0 to m here. Remember, b is really, negative infinity. Oh my god, I forgot the negative. Make sure you fix that. That's negative infinity. And here, m represents infinity. So I'm going to the left forever and to the right forever. Now let's keep going here and let's actually plug in our 0, our b, and our 0 and our m. Before I plug in, let's just go ahead and rewrite it without a negative exponent. So I'm going to kick this into the denominator to make that exponent positive. I did that for both. So I'm going to plug 0 in, and then I'm going to plug b in for x. I'm going to keep the negative 1/2 with it. Before in the example we just did, where's my cursor? We took negative 1/2 out and we did everything. I'm going to keep it with it. It'll be the same either way. You can factor it out if you really want to and see if we get the same thing. So I have negative 1/2 e to the 0 power minus negative 1/2 e to the b squared power. So pause if you need to make sure you're okay with what just happened there. And then I'm going to let m go to positive infinity here. So I have negative 1/2 e, plug m in first, m squared, minus negative 1/2 e, plug 0 in to the 0. Let's see which of these we can evaluate easily. E to the 0 power is 1. So I have the limit as b goes to negative infinity of negative 1/2 minus the negative is positive 1/2 e to the b squared. And let me finish cleaning this up. So I rewrote this last bit, minus a negative is plus, this is 1/2. So now that we've done everything, we're ready to actually do direct substitution with our limit here. So I'm going to plug a negative infinity in here, and I'm going to plug an infinity in here. Now, first of all, this is just going to be negative 1/2 because the limit can't touch that. It's just going to be negative 1/2. If I plug a negative infinity in here and square it, that'll be a positive infinity. E to the infinity is huge. 1 divided by a huge number, 0. Now, infinity squared is infinity again. E to the infinity is a huge number. Negative 1 divided by a huge number goes to 0. I'm just left with 1/2. In this case, it ended up being 0, which makes sense if you look at the picture, but again, you do not want to assume it's going to be 0. So our limit exists. We have a convergent integral here, and the area under the curve is 0. Our last problem for this video is the improper integral from 0 to infinity of 4x e to the negative 2x. This is the graph of it. I'm going from 0 to infinity. Now, you might be thinking, hey, this area looks a lot like the one we just did. And in fact, the integrand also looks pretty similar to the one we just did. The key difference is here, I had a higher power and a lower power, whereas here I have equal powers and then exponent and on the bottom here. We cannot do u sub because if you try to let u be the exponent, then du will be negative 2, and there's this x going around that we wouldn't have taken into account. So we're going to have to do parts. Now, I know you have this formula near and dear to your heart and it's already memorized, but just to remind yourselves, this is it. I'm going to call something in the integrand u and something dv. So I called u 4x dv e to the negative 2x dx. I found du and v. Following Lipet, I have a polynomial term that was 4x. So I went ahead and completely ignored this limit. Limit is just hanging out. I only took this with an integral. I'm in fact ignoring the fact that I'm going from 0 to b at all. This is all on the side here, just getting an actual antiderivative, and then I'm going to remember, oh, okay, it was from 0 to b, and b is going to infinity. So don't just blindly copy this work down. Pause the video, write this down, make sure you remember how to do u times v minus the integral of v du. I cleaned this up, 4x times negative 1/2. and I cleaned this up and did an antideriv. I'm going to finish this up in the third video,